Welcome back again. So we've talked last time about brushed DC motors, so that's not the goal this time. This time we're going to talk about steppers, and then next time we'll do servos. So stepper motors, let's talk about these guys. Stepper motors work very, very different than DC motors. DC motors, you give them power and they spin as fast as they can, and that's what they do. Stepper motors, the way they work is you give them a signal and they move one step, and if you don't change the signal, they will never move, right? So they will only move if you give them a new signal, and they'll go one step and stop, and then you have to give them a different signal and they go one step and then stop. So if you wanted to do like a full revolution of a stepper motor, you might have to send it like 200 different signals, and it's up to your microcontroller to send it a message and to know how long it takes to get there, and then to send it another message. So they're much more complicated to control, but there's some real advantages to steppers. So let's go ahead and take a look and see how they work. So the way they work is kind of opposite of DC motors, because they have their permanent magnet is on the inside. So their permanent magnet spins, which is the exact opposite of DC motors, right? And what it does is you'll have coils on the outside. So let's say that this one right now has a south and a north, so it's there. And then all of a sudden, if you changed it, you put a south and the north here, then what would happen is it would rotate this inside, towards that next spot, right? So it'd kind of hover here in the middle. And then as soon as it was happy there, it would come to a stop. Your microcontroller would say, hey, it needs to move some more. So let's just say it would swap, let's swap this top guy. So let's say he became a north and he became a south. Then all of a sudden it would rotate farther, and that north and that south would move to go to that spot. So they're quite simple. They have an electromagnet on the outside, and that causes the permanent magnet to spin. So it's the exact opposite of how DC motors work. There's a lot of really good animations. Here's one, just to kind of mention it. It's hard for me to draw these things, but I mean, you can see on here what's happening, quite well. If you, chase, the north of the south as it goes around in this little animated GIF, you can see how it'll move. So much better drawing than I can have. This link, by the way, if you were to actually go to it, it's got a lot of good information on there as well. Now, the way they really work is on this diagram, you can see that every time it moves, it's going like 45 degrees. That's not the way a real stepper works. This animation is more of what a real stepper, how it works. It's actually got lots of little norths and souths, like little teeth. And every time it moves, a typical stepper will go 1.8 degrees. I'm not sure who picked that number, but 1.8 degrees, like most steppers you buy, each step is 1.8 degrees. So that means it takes 200 steps to go all the way around. And so that's kind of how most of them work. Now, that's how it really works, but to keep it simple, I'm going to always kind of look at the one that turns a full like 45 or a full 90 because they're easier to describe. But know that in reality, they actually look, like this hybrid thing. There are actually a lot of different ways to drive them. Let's just go ahead and look at a quick little video. Specifically, this is about half step, but I don't really care about that. I just like their animation. And you can see that the permanent magnet in the middle, like the arrow represents north. One way you could do it is you could excite only like half of a phase at a time, is what it's called, and it would simply go to wherever that single excitation is. Another way you could do it is you could excite two of them, and it would kind of shoot to the diagonal between them. And so that's kind of the way that you could control this thing. I'm getting ahead of myself a little bit, though. Let's go ahead and talk about wiring and how the wiring of these things works. So the wiring of these things, you can control them in two ways. One way you can control them is with 4 MOSFETs. So 4 MOSFETs is one way you can do it. That's called unipolar drive. So that's the unipolar mode. Another way you can do it is in what's called bipolar mode, and there you use 2 H-bridges, which works out really nice because our H-bridge chip, like the L298 or the 754410, it actually has 2 H-bridges on one chip. So these are your 2 options. You get 4 MOSFETs is one way you can do it, or with an H-bridge, and bipolar is another way you can do it. Now it depends a little on your motor, which way you're going to drive it. If your stepper motor gives you access to only 4 wires, so if it's a 4-wire stepper motor, your only option is bipolar. So you've got access to 4 wires. Essentially you've got, in that other drawing, you've got a wire coming out here and here, so this would be like, 1 wire or 1 set of wires, there's the other set. If you've got 4 wires, you have to use bipolar control. You have to use 2 H-bridges. That's the only way you can do it. If your motor, so what they do is they can also give you access to the wire, like right here, it's called a center tap. So like this would be like a pin 4 and a pin 5 and a pin 6. If they give you that center tap to like where you can individually control the phases, it would look something like this. So it could be an 8-wire where you have like access to absolutely everything. It could be a 5-wire where they've got all the center taps together, or the ones that we use in this class are 6 wires. The way you could wire a 6-wire stepper is with 4 MOSFETs. So that's one way you could do it. And what you would do is you would just put, the unregulated 5 volts over here, and then you would have 4 MOSFETs to drive it. The advantage of this is the MOSFETs we have are good up to like 2 amps, so that is an advantage. The disadvantage, just to mention up front, is they're half torque. So you get essentially half the torque that the stepper motor could be giving you, because the way they work is you're using either this coil or the other coil, but never both. So you're not using the entire coil, you're using half of the coil. So it is a half torque. That's the downside of it. So what we choose to do is, even though our stepper motors have 6 wires, like we can run them in unipolar mode, we certainly could. We choose to do it in bipolar. Oops, I said bidirectional, I meant to say bipolar. And so let's just kind of show how we would do that. So instead of that guy right there, let's take him off. What we can do is we just connect this guy right there. So this is kind of like pair number 1. And then we connect this guy right here. And that's pair number 2. And we just we do not connect 2 and 5 at all, right? We just don't use them. So what this lets us do is this lets us activate a coil to where we can use the entire wire. What that does is that gives you the full torque capabilities of this stepper. So bipolar, full torque, good. Makes you use an H-bridge, bad, because we can destroy our H-bridges fairly easily. But this is what we're going to do in labs, so this is probably what you care about the most. So you're going to have to figure out when you physically get one of these stepper motors in your hand, you're going to have to figure out which wire is which. The pins on here may be accurate, like it may be 1, 2, 3, 4, 5, 6. Maybe you can count on that, maybe you can't. Turns out it probably works. But if you buy one, the best way to test it is actually just to get a digital multimeter and just measure the resistance. So for example, if I grabbed 1 and 3, I might see like 8 ohms, whereas if on a different day I grabbed these 2, I would see like 4 ohms. And of course, if I grabbed somebody that didn't connect, like let's say I grabbed this guy and this guy, I would see infinitely many ohms because it's not connected. So even if you don't know how it's connected, You could always use a digital multimeter to figure it out. And then what you want is you want to use the ones with the higher resistance. So like that would be good. Those would be the ones you want because we're going to use it in bidirectional mode. It sounds confusing until you kind of figure it out, right? So here I'm gonna do what you're gonna do in lab, right? So to connect this thing, I've got an actual H-bridge chip. So this is the H-bridge chip that we're gonna use. You're gonna connect one side to the right, and then you're gonna connect the other side to the left. And what people call these is they call it like phase A and phase B. I don't really care about that. And then this other side is just going to be intentionally open. So this is how you're going to wire it up for bipolar mode, which is what we're going to use in labs. For your project, if you want to use unipolar mode, you go nuts. There are some advantages to it that you can use MOSFETs, but this is what we're going to do in lab to drive these things. Then, of course, you've got to control it. Which is kind of important. And so what we're going to do is we're going to pick a strategy. There are multiple strategies, and this is unipolar or bipolar. Both have these strategies. There is a strategy called wave step, where you have like either the left side H-bridge on or the right side of the H-bridge on, but never both at the same time. Which we're not going to use. There's one called full step, which will have the left side and the right side always on. It's just a matter of whether they're on this way or that way, and it's going to switch is the way it's going to work, and that's going to make it go around. There's also something called half step, which toggles back and forth between wave and full. The advantage of that is instead of 1.8 degrees, you actually get 0.9. So you get slightly better resolution with half step. There's also something called micro stepping, where you don't give the coil full strength and you can actually do an infinite number of positions, but I don't really care. So there are all these options, but I'm going to pick full. Why do I pick full? I pick it because it gives you the full torque, right? So you're always using essentially all 4 coils all the time. You're just switching how they're being used. So we've picked a strategy, full. We've picked bipolar. Let's actually look at the pattern for full. I think I said this. So you're always going to have power on one side, ground on the other. It's always going to be active. Your motor's going to essentially be on these diagonals. So the south will be here, and then here, and then here, and then here. So there are essentially 4 steps. So 1, 2, 3, and 4 as you go around, and it's going to always be kind of on a diagonal. If you were to look at it from a timing chart perspective, I'm not sure if this helps you or not, but you're always going to have pairs. So you'll notice these 2 are a pair, so they're always opposite. And then these 2 are a pair, they're always opposite. These represent like 4 signal lines coming from your microcontroller. And what you'll notice is one of them changes while the other stays the same. It's like either this pair changed or that pair changed, and so that's how you drive a stepper. So you have a pair that goes, and then the other pair goes. All right, that was not a great explanation, but we'll get there. Maybe this explanation will help you more. So this is a real circuit. So first off, I'll go ahead and wire it. So kind of the same as before. I'll wire my motor first. Oops. And then I'm going to wire my pick second. So let's say my pick, let's say I wanted to use RB0 to control the enable line. You could, if you wanted, pull the resistor to 5 volts to make it always enable. Instead, I'm going to control it from the micro. The reason I like to do that is because when you stop moving, if you bring the enable line low, that takes no current. Otherwise, a stepper pulls just as much current if it's moving or not. So if it's enabled, it's pulling a certain amount of current, period. But if you disable it, then it can stop moving without pulling current. So I like to control the enable line. So I'm just going to say RB0 is my enable line. So then next I've got a pair. So let's say I've got this pair controlling one side. And then I've got my RB3 and my RB4 pair on the other side. The nice thing about pairs is it doesn't even matter how you wire them, right? So just make sure you get the pair on the left and the pair on the right. I don't care about, once it starts moving, then we'll decide whether we want clockwise or counterclockwise. Don't even care about the pairs yet. I just make sure I keep my pairs together. So if I wanted to drive this thing through a full step, first off I would need RB0 set to 1, just so it moves at all. And then, like, I might have a starting off position there. You'll notice that my pairs are always opposites. And then as soon as I want it to move, I'll switch one of them but not the other. And then for the next step, I'll switch one of them but not the other. And I think you've got the idea. You switch one of them but not the other. And so then the pattern repeats, right? So then you would loop back around to the start. And if this pattern made you go clockwise, then doing the pattern in the other direction would make you go counterclockwise. So that's how you would go the other way. So this is how you drive a stepper. I think that this diagram here makes the most sense to me, and the others kind of got me confused until I got to this one. And then it kind of all came together for me. So there are pros and cons of steppers versus DC motors. First I should say where you buy them. So you buy them at the usual suspects, right? So Robot Shop, I picked some different links than I picked last time. They sell steppers, right? I cheated and made a direct link here. Really you would have to go to Robot Parts, motors and actuators, and then click on the word steppers, right? So that's one. I mean, all electronics sell steppers. You would get there the same as before. You would find motors, and then for motors, you would click on steppers, and there would be a whole bunch of steppers. I had a really bad run with students buying small steppers. Typically, like, if the wires look big, like this one, the wires are kind of too big, it's probably not going to work well. This is like a really, the torque on this thing is so bad. So I will give you the warning, this one's just not going to turn anything. This one's going to be better. Typically, if the wires look big, this is really small and it's going to be terrible. If the wires look small, it means the motor's actually big, and it will actually have some chance. But I mean, you can buy these things anywhere. I mean, if you wanted to go to SparkFun and just type in stepper, I mean, you'll find a whole bunch of steppers, right? So a lot of good options. The thing I dislike about steppers is their torque is not as good per dollar. So here's kind of a compare and contrast. So typically at a reasonable price, you're going to get lower torque with a stepper. They are nice in that you can go as slow as you want, so I do like that. They do not go as fast. Well, you get like 1 rev per second. They do require both sides of an H-bridge, the way that we will teach you to use them. You could also do it with 4 MOSFETs. Most of them operate at 5 volts, which is just kind of nice, actually. There is a more complicated control strategy. That one doesn't really matter so much because you're going to get so good with this pick that you won't even care, right? So you'll be able to do it. And then the number one selling factor, the reason you would ever use a stepper, you've got full position control. So if you need to go to an exact position, it is only relative. Like, it only knows relatives, it has no idea where it's at. Absolutely. But if you need relative position control, man, they do it, right? Gearhead DCs, just to kind of continue the compare and contrast. So much higher torques. This top bullet is the most important to me. If you need torque, you're going to have to go with the Gearhead DC motor, right? So like, and Sometimes that's the only thing on this list that matters. If you need torque, you have to go with it. You can get exact positions with the gearhead DC. You just have to have some other sensor, like a brake beam sensor or an encoder if you want to be really fancy. But that high torque is what makes gearhead DCs the dominant favorite in this class. There's a time and place for steppers. They do need a gearhead. There's absolutely no feedback about speed. So you just turn the thing on and it just goes. That's the downside. They do come in a variety of voltages. The biggest negative is that the H-bridge we use to control it bidirectionally is only good to like 0.5 amp. So it's sometimes hard to find an H-bridge that will control it. We do have some other options for you, but in your projects, if you buy a really fancy motor, the only thing that really fancy motor is going to do is going to destroy your H-bridge chip. So you've got to think these things through. You've got to have a certain size motor that meets your torque. You've got to have a transistor that can turn on and off that much current. And then, of course, you have to have something to control it all, but that's usually a little bit easier. So those are kind of some of the pros and cons. All right, hopefully you've got some knowledge about steppers. That's all I'm going to say about them. We'll use them in class, and that's when things will really come together for you. Next time, what we're going to talk about is servos. See you then.